Let's move on to chapter 3. Let's talk about linear motion. And then in the last 10 minutes, I'm going to introduce you to what our experiment will be on Friday, and I'll let you read over it. I'll post it on Canvas too. Let's talk about speed first. So speed is the distance over time. So you basically, if I drove 100 miles and it took me 2 hours, then I was driving at 50 miles per hour. Here are some useful conversions between them. I'll often use meters per second because it's SI, but if you want a conversion to miles per hour, here's the conversion. At 5 meters per second, it's about 11 miles per hour or 18 kilometers per hour. It's about the conversion here. So like walking speed's about like 2 meters per second or 3 meters per second. And here I'm not really worrying about direction for speed. Now instantaneous speed is what this is like the average speed right here. This is the average speed. Whoops. Average speed. It's not what the reading is at any given instant. But if you're looking at speedometer, that would be the instantaneous speed. The speedometer reading. So it could be either in miles per hour or meters per second, kilometers per hour or meters per second. This has these two here on this reading here. Okay. Questions so far? All right, let's go ahead and move on to velocity. So velocity is the instantaneous speed and a direction. Velocity, a vector quantity. So we need the instantaneous speed and a direction. So constant velocity is when the acceleration is 0. When the object occurs, I should say, occurs when the object has no net force on it, i.e. equilibrium, is in equilibrium. Okay. So velocity could change if the speed or the direction changes. This means that there is an acceleration and a net force on the object. As long as we're in Euclidean Newtonian dynamics, at least. I'll do that little caveat because, well, Einstein made everything a lot more complicated, more exactly what it is, but it's more complicated than that, so. All right. Let's do an example of a cart going in a circular track with a constant speed. Is the velocity constant? Is the velocity of a car moving on a circle at constant speed constant? What do you guys think?
I mean, it depends on the size of the circle, doesn't it? And the speed. If you're going really fast, you're not really going to be able to be inside of a small circle.
So you're getting the practical things, and yeah, it's gonna be harder to be if you're having a tighter circle, smaller circle to pull it off. But I think you're not quite. So that's not quite the question I asked though. Uh, is the velocity constant though?
No,
Why? And you're right. Why?
because you're constantly turning,
Mm-hmm.
you're changing your direction.
Exactly. Yes. The direction is constantly changing. Changing. And that is an acceleration. Even though the speed is the same as it goes around, the direction is changing. So therefore there's an acceleration. You can think of like the length of the vector is changing, is staying constant, but the way it's pointing is changing. Yes, Addie.
Ah, wouldn't the constant direction, well, can an arc or a slope then be a constant direction, or is this just any? I don't understand how direction is being used here because I just imagine this being a constant direction, this degree of change.
Uh, the answer is so here, like if I draw like this right here, let's go ahead and make it a little bigger. Like this would be my vector right here, pointing right here. This is my velocity vector here. At some later time here, it points this way. I'm gonna try and do the same length. It's too long. So it's the same length, but now it points this way. So it changed its direction. So now it's no longer pointing in the same direction. And then here, it now points like this. More like this. Trying to draw in 3D here. Like this. That makes sense, Addie? As it goes around?
I understand what you're saying.
So a circle wouldn't be in equilibrium?
If an object is traveling along a circle, it cannot be in equilibrium.
Yeah, okay. So velocity can only be in a straight line then? Okay, I think that's what Addie was trying to ask.
Yeah. If you're in equilibrium, your velocity is going to be in a straight line and have the same length the entire time. For an object to be in equilibrium.
But a vector doesn't have to be a straight line, or it does.
Yeah, a vector is just speed and direction.
Okay.
Right.
Any speed in any direction. Velocity is only an equilibrium in one direction.
I know.
No.
No.
No, so a velocities, we say the velocity is constant if you're in equilibrium. Yeah. So the velocity can change, but to be in equilibrium, it can't change.
But a vector is just a measure of a velocity.
It's more like velocity is a kind of vector. There are other vectors too. There are also force vectors and acceleration vectors. An object to be in equilibrium, the velocity vector can't change its length or its direction. Okay, other questions? By the way, we can't feel velocities. Just like in that video I showed you guys, you can't really ever feel a velocity. But what you can feel is an acceleration, a change in velocity.
So a vector is just speed and direction in terms of velocity.
Well, yeah. So velocity is a speed and direction, yes.
Okay.
It's 2 meters per second to the left, 30 kilometers per hour south, things like that. So this one actually has changed direction. Here, let's say this was east. This is like, then this was like, this is east. This would be like south. Then this would be like north here, and so on. See, the direction's changing the entire time. Assuming like this was north and this was south here. So I'm saying even if the length of the vector is the same the entire time, since the vector is changing its direction that it's pointing, there must be an acceleration. Okay, so acceleration. I think we'll end it on here then. And I'll go over the lab a little bit. That we'll do tomorrow. Friday, I mean. So we can change the velocity of something by changing its speed, changing its direction, or by changing its speed and direction. Any one of these three cases will be an acceleration. Like, have you ever had a car turn and you get like thrown out on the curve when you turn really sharply? That's actually, you're trying to go in a straight line, and the car is actually pushing on you with either the seat or, you know, if you're going really fast against the side, you get slammed up against as the car turns. So the car is accelerating you to turn you. Or it can do both. It can change its speed and direction too. So we can say an object is accelerating when its velocity is changing. It's a change in velocity over the time interval. So I'm going to just go ahead and this little footnote here, which is kind of important, so I'll go ahead and talk about it from your textbook. The phrases change in and difference in can be represented by the Greek symbol delta, and I'll use that. We can express the acceleration as delta v over delta t, where delta v is the change in velocity, and delta t is the corresponding change in time. This is going to be the average acceleration. Now, remember how I said that velocity has to be a vector? So you'd have to do may have to do a triangle geometry here. And if we were doing a more mathematical class, I would have you do more geometry. But we'll go ahead and keep it mostly straightforward now. Most accelerated motions in this book will be of constant acceleration, like objects falling, having the gas pedal at like a constant rate, and things like that. Okay. I think I'm going to go ahead and come back and we'll review acceleration on Friday, but I want to go ahead and talk about our lab that we're going to have. Any questions, though, before I stop for the day here? And then I'll talk about the lab. Okay. So Friday's lab. By the way, usually I'll have it on Wednesdays, but just today, this week we'll do Friday. Have you guys introduced to things. So you should use this